My name is Agnishom. Today I am going to present my work on verified matching for regular expressions with Lookaround. This is joint work with Konstantinos, Mamouras and Angela Lee. Textbook regular expressions consist of union, concatenation and clean iteration. However, in practice with tools such as PCRE or grep, there are a number of additional features available to the user. Examples include counting, which would make the regular expression more succinct, or back references, which might add some form of non-regularity. Today we are going to talk about lookarounds, which provide a way to do contextual matching. Let's consider an example. We are interested in extracting the area code from a US phone number, which happens to be the first 3 digits of it. The expression here extracts the first digits, but the lookaround also makes sure that the entire string is formatted correctly as a phone number. Lookarounds also appear in other kinds of common regexes. For example, the beginning or end of string markers are a form of lookaround, which checks that there is no additional part of the string in front of or behind the current position. Word boundaries are also lookarounds, which check that the position being matched is at the end of the word. Here we describe the contextual matching semantics using for lookaround expressions with lookarounds. The expression on the screen denotes the window from I to J being matched by the expression R on the word W. Lookarounds form windows of 0 width at a specific location. To match positive or negative lookaheads, the window spanning the current location to the end is taken into consideration. To match lookbehinds, the window from the beginning of the string to the current position is used. We use an inductive predicate to encode the semantics of matching for expressions with lookarounds. Working with negative lookarounds is slightly more difficult. The obvious solution here is to encode a construction which accepts a proof of the negation, but this is not accepted by Coq due to strict positivity requirements. Our solution is to use 2 parallel predicates, one denoting matching and another denoting not matching. Later in the theory, we show that one is the negation of another. With the help of our semantics, we can perform some simple equational reasoning. This requires 2 definitions. The notion of regex equivalence says that 2 regexes match exactly the same windows on exactly the same words. The other notion of inclusion says that the first one matches a window on a word, then so does the second one. With this framework, we can verify that just like the classical regular expressions, expressions with lookarounds also satisfy the Kleene axioms. This involves checking the semi-ring axioms on the structure formed by concatenation and union. In addition, we also have to verify certain laws involving Kleene iteration. We have also verified some properties specifically about the lookarounds. First, we can show some simple algebraic properties such as the commutativity and idempotence of concatenation of them, or their distributivity over union. In some cases, we are able to flatten the lookarounds. Another observation is that the lookarounds can be shortened by intersecting the predicates that they use. This transformation could be repeatedly used in order to remove lookarounds of bounded width. Let us take a brief look at the landscape of regular expression matching. A common approach is to use a backtracking based matcher. These can be exponentially slow on the worst case input. For example, for this expression and this input, the engine would have to explore all possible choices across all unions before finding the correct combination of them. Backtracking based parsers are used by engines like PCRE2 or grep. They are also packaged with a large number of regular expression libraries with programming languages such as Java or JavaScript or Python. The other approach is to compile the regex into a finite state machine. The advantage of this approach is that they can be simulated in linear time, and this is used by regex engines like Google's RE2 or Intel's Hyperscan. However, this approach is less flexible. On the other hand, it is easy to add features such as back references or lookarounds into backtracking parsers. In the work that we present, we have produced a formally verified regular expression matcher which supports lookarounds. It is efficient in the sense that the time required to match is linear in terms of the size of the regex and the input. Let us illustrate the matching algorithm with the help of an example. Let us consider this regular expression. It has a top level look ahead. Inside this look ahead, there is a nested look behind. Our algorithm decomposes the regular expression into multiple layers, one layer for each look around. At the very bottom layer, we have the expression R0. This expression is looking for the presence of a C in the past. Above this layer, we have the expression R1, and notice that this contains an oracle query marked as Q0. This refers to the fact that the sub-expression has already been separated as R0. Since this is a look ahead, the regex must be matched on the future of the current position. Finally, we have the top level expression R hat, which has the oracle query Q1. Consider the word ABCDE. For the look behinds, we are interested in the question, does the window from 0 to the current position match? And for look aheads, we are interested in the question, does the window from the current position to the end of the string match? First, we start with R0, and this is something which can be matched using the string itself, using usual automata theoretic techniques. And then we match R1. R1 has the oracle query Q0, and whenever this oracle query arises, we use the information that was computed while matching R0 to resolve these oracle queries. Then we match R hat, and doing so requires the information which was produced while matching R1 in the same way. Let us summarize this algorithm. The main idea is to decompose this expression into layers. Each layer represents a level of a lookaround. This decomposition produces regexes with oracle queries. We are going to call them O-regexes for short. When the upper layers are matched, they may use information from the layers below. Thus, we need the string package together with oracle valuations. We call this data structure an O string. Thus, the main workhorse of the algorithm involves matching O regexes on O strings, and we do this in a layer-wise manner starting from the bottom, using information from the previous layers to resolve the oracle queries. For the layers with look behinds, we wish to know for each I if the window from 0 to I matches, and this is done with a simple linear scan. For the layers with the look behinds, we wish to know if the window from the current position to the end of the string can be matched. It is possible to obtain this information using a single linear scan. This involves scanning the reversed regex on the reversed word. The correctness of our algorithm can be formally expressed by making the connection between expressions with lookarounds and O regexes more explicit. Given an expression with lookarounds, we consider the top level lookaround it consists of. Here we have the sub-expression M. We have a string on which we intend to match the lookaround expression. By replacing the maximum lookarounds with oracle queries, we obtain an O regex. This O regex must be matched on an O string. This consists of the original string packaged together with oracle valuations. These oracle valuations indicate whether the window from the current position to the end would be a match for the sub-expression M. O strings are strings with oracle valuations. These valuations comprise a list of booleans. Each boolean corresponds to the result of a maximal lookaround. It is useful to visualize O strings as alternating oracle valuations and letters. Since each letter is surrounded by oracle valuation on both sides, this means that there is always one more oracle valuation than the number of letters in an O string. The concatenation of O strings is defined only if the oracle valuations at the end of the first word and the beginning of the second word agree. In the example shown, beta n must be the same as the valuation gamma naught in order for the concatenation to be defined. This is a difficulty in Coq. So to avoid this, we, instead of defining concatenation, we define slicing. Instead of writing let x equals u concat v, we would say that u and v are produced by slicing x at a certain point. Instead of lookaround expressions, O regexes contain oracle queries, which we denote using the notation qi. Recall that each valuation is a list of booleans. The oracle query qi tests that the ith entry of the current valuation is true. Note that the concatenation of O regexes correspond to the concatenation of O strings. Therefore, when we have concatenation of two queries, they behave like a conjunction. Here we illustrate how O regexes behave with the help of some examples. For these examples, let us say that we are dealing with a scenario where each valuation consists of two boolean values. The single character regex A or B corresponds to an O string containing the letter A or B. There is no restriction on the oracle valuations that they are surrounded by. Let's consider the regexes Q1 and Q2. These will be satisfied by O regexes of length 0. That is to say that these O regexes contain no letters but a single valuation. The query Q1 or Q2 assert that either the first or the second entry in this valuation must be true. Consider the regex A, Q2, B. Here the valuation between A and B is being restricted by the constraint Q2, which is asserting that the second boolean in this valuation must be true. Next, let's consider the situation where this Q1 has been added to the front of the regex. This asserts that the first boolean in the extreme left of this O string must be true. In the last expression, Q1 and Q2 both appear between A and B. Since they are referring to the same valuation, both of these booleans must be true. As we discussed, the workhorse of our algorithm involves matching O regexes on O strings. Let us discuss the possible avenues for implementing and formally verifying an algorithm for this. One possible way to deal with this is to match using derivatives. This technique is purely functional and can be elegant. In the last year's CPP, Zhushko et al. Verified their algorithm for matching lookarounds in Lean using the notion of location-dependent derivatives. The difficulty with this technique, however, is that the derivative size can grow rapidly with the number of characters in the input string. Thus, one has to carefully keep simplifying their expression in order to keep the size manageable. Another way to solve this problem is to simulate an NFA directly. Our original work on this problem used the notion of an enriched NFA, which had transitions guarded with oracle queries. Unfortunately, formalizing an NFA simulation can be quite challenging. This is because we have to reason about graphs and paths in these graphs. Additionally, an NFA simulation algorithm would require tracking the set of active states, which is usually done using a mutable array. Our approach is based on the notion of marked regular expressions. This idea can be seen in functional programming folklore, and a nice exposition can be seen in Fisher et al.'s ICFP 2010 paper. We have extended this idea to deal with oracle regular expressions. The key idea here is to mark letters in regexes to represent active states of the NFA. This is a structured way to represent an NFA together with its active states. Instead of representing the NFA using a separate graph, we use the AST of the regular expression itself. A marked O regex is similar to an O regex, except that it may contain marked letters. Notice that we do not allow marks on the oracle queries. We illustrate the main idea behind marked expressions with the help of an example. The NFA on the right corresponds to the O regex on the left. Notice that this NFA has certain transitions which are guarded with oracle queries. These transitions are enabled only if the guards are satisfied. Initially, only the first state is active. We denote this with the token on an NFA and by marking the letter on the left. On the partial input shown on the screen, both of the states are active. Therefore, we mark both these positions in the corresponding regular expression. Upon receiving an additional B, the state immediately following the transition marked A is no longer active. This is also reflected in the markings of the O regex. In this way, the markings on the regex reflect the active states of the NFA that it is simulating. Marked O regexes are a purely functional way to simulate an NFA. The marks correspond to active states in the NFA simulation. Similar to the technique of regex matching using derivatives, we use a few functions to manipulate the marked O regexes. First, we have this function which can check if the given expression accepts the empty string. There is the function isFinal, which checks if any of the final characters in the regular expression contain a mark. If this is so, then the given input has been accepted. The function init marks the initial letters. This corresponds to the idea of placing a token in each of the initial states of the automaton. The function shift follows the transitions and moves each mark to the next letter. This is similar to the idea of moving each token on the NFA to its successor state. The function read removes the marks from the letters which do not match the current input character. For the purpose of verification, we assign a notion of semantics to these marked expressions. The denotation of each marked expression consists of the language of words which can be accepted from the marked letters, starting from the marked letters. For example, if we have the regex AB star with the initial A marked, then the denotation corresponds to the language AB star itself. This is because A is an initial character here. Now consider the case where the B is additionally marked. This corresponds to the case where we could also include letters, the words of the form B star, which we obtain by starting from the letter B. Finally, if none of the characters are marked, then the denotation of this is the empty set. This is because there are no active states in the automaton that it represents. Let us briefly look at the algorithm involving how marked regexes work is verified. The main idea is to prove several characteristic lemmas. This involves how functions shown in the previous slide, such as init, shift, read, and so on, change the denotation of the marked regular expression. Nipkow and Treitel have previously used a similar proof technique in their ITP 2014 paper. The main challenge in our setting is that we must deal with oracle valuations. The functions init, shift, and so on require an additional argument in many cases, which is related to an oracle valuation. The characteristic lemmas themselves are also harder to state and less clean. This is because the queries do not carry any marks, and sometimes we need to carefully characterize the valuations that appear on the extreme left or extreme right of the words. We have extracted our coq proof scripts into executable Haskell code. Our goal is to empirically evaluate the claim that our algorithm is linear in terms of both the length of the input as well as the size of the regex. We have chosen a family of regexes. We can see here that with the increase in the parameter, the size of the regex increases linearly. For these families, we have chosen an input which would elicit the worst case behavior in backtracking based matchers like PCRE. In this plot, we have shown the total time taken to process the string given its input length. The different lines in the plot correspond to different values of the parameter. We can see that the increase in the input string length, the time grows linearly. In the next figure, we fix the size of the input string and show the time taken to match the string for larger and larger regexes. Each line corresponds to a fixed size of the input string. Again, we see that the time taken increases linearly with the size of the regex. We have also observed that the tools such as PCRE exhibit superlinear growth for these regexes. I want to conclude by summarizing the key points of this talk. We have presented a formally verified regular expression matcher which can handle lookarounds. The proof script consists of about 10,000 lines of coq code. The main idea of the algorithm was to process the lookarounds layer-wise. We match the regexes inside the lookarounds first. Then we use the pre-computed information to resolve the lookarounds. The main abstraction we used was the notion of O regexes and O strings. Thus, we solved the problem of matching regular expressions with lookarounds on strings by matching O regexes on O strings instead. We did this using the technique of marked regular expressions, which are a purely functional way to simulate NFAs. We retain the same efficiency guarantees as that of the original algorithm, namely that it is linear in size of the string and the regex. We have empirically confirmed this by performing experiments on the extracted Haskell code. The proof scripts for this formalization are publicly available. Thank you for your attention.
I don't think. Oh yeah, thanks so much. So I guess the question is the speaker online? Oops, is the speaker online?
Yeah.
Okay, perfect. So are there any questions?
Hi. Yeah, thanks.
Hey.
No?
Hey,
All right.
yes, please.
Yes. Okay, great. So cool stuff. You said a little bit about equational reasoning using these lookaround clauses.
Yeah.
Is there any hope at all for a completeness theorem in the same style of Cozen?
I believe that should be possible, but at this moment we do not have this, but I think we are working on it.
All right, thanks.
I do not have many details right now. Thanks.
Yeah.
Hi.
Any other
I have a question
questions?
about the complexity of the algorithm with respect to the size of the alphabet. Because you were showing examples with sort of simple examples of A, B, and C, but I'm just more curious about, let's say, if you take Unicode or real regexes, how would you partition the essentially the predicates that occur in the regex with respect to your algorithm?
Yeah, so maybe I should summarize the question. I think the question is about like, does the size of the alphabet affect the complexity? And the way we have encoded this algorithm is the regular expression to carry predicates. So the atomic elements of the regular expressions are Boolean functions which will be executed on each single letter. So as long as those functions can be executed in constant time, like the rest of the guarantee should remain.
I was more thinking about typical regular expressions that, for example, involve, character classes like, is a word letter or is it digits or intervals.
Yeah, we should be able to do character classes with the same complexity.
Okay. Then
So
I have another question, which I'm wondering about. You mentioned that when you compare to derivatives, that the downside or
yeah,
the vice of derivatives would be that the size grows. But I don't quite
yes.
see that, because depends on what kind of derivative you're looking at. If you take Brzozowski derivative, then you're essentially doing incremental determinization. Then, of course, you're building a DFA. But if you take an Antimirov derivative, then the number of derivatives is actually linear in the size of the regex you start with.
Yes, I think that's true. We could do anti-Mirov derivatives. In fact, like this would be a NFA simulation in disguise, but then we would have to have like the machinery to manage sets and so on. This is why we did not go this route.
Okay, thanks.
Yeah, thanks. Any other questions?
Hi. Yeah. So your when you're calculating these lookarounds, did you consider like doing a well, I guess it's a sort of dynamic programming algorithm. Did you consider doing memoization instead, so that you didn't have to calculate all of the oracles? Because I would guess that in a lot of situations, you had an example where you had D, E, and then Q1. Unless you have a D and an E, you're never even going to ask what Q1 evaluates to. So you might save a lot of computation that way.
Yeah, that's true. So we have not done this sort of thing for this COG formalization to keep it simple. But I believe the original paper from last year's POPL has many of these optimizations. And also, I believe there was a version of this algorithm presented somewhere last year, which was based on memoization. It like the authors were Fujinami and Hasuo. So I think that approach is based on memoization rather than going bottom up.
Great. Thank you. Thank you
Yeah,
for your
thanks.
talk. Maybe as a suggestion for next time, it would be great to turn on your camera so we would actually see you when we talk to you.
Okay.
Yeah. And we'll move on. So maybe give him a hand of applause. It was a very nice talk.